Well, today we've talked a lot about AI, right, in the afternoon, in the evening. But I also know that a lot of guests are here today to listen to the next keynote speech. So, in a minute, we're going to welcome our keynote speaker, Dr. Vamsi Boppana. Let me introduce him first. Dr. Vamsi Boppana is responsible for the AI strategy across AMD, including driving our AI roadmap across client, edge, and cloud, execution of the AIE IP and product roadmap, as well as growing our AI software capability, including the unified AI software stack, AI models, and use cases. Until 2022, Boppana led the Central Products Group, CPG, for 4 years at Xilinx and AMD. Before leading CPG, Boppana joined Xilinx in 2008. Boppana earned a Bachelor of Technology degree with honors in Computer Science and Engineering from the India Institute of Technology, IIT, and a Master of Science and Doctorate in Electrical Engineering from the University of Illinois at Urbana-Champaign, UIUC. So, without further ado, ladies and gentlemen, let's welcome Dr. Boppana.
Good evening, everybody. Much better. First of all, I want to thank the CIE for giving me this opportunity to share my thoughts. It's a huge privilege to be here amongst a distinguished company. Actually, this is one of my favorite venues. This is the place where I gave my very first talk, almost 31 years back, as a graduate student. And I, as an immigrant engineer myself, I can relate to the mission of CIE that helps young engineers meet their ambitions and realize their dreams in this great nation. So thank you, CIE, for making that possible. Big hand to CIE. So tonight I'm going to share just a few thoughts about an incredible transformation that is happening in our lives. You heard about AI being mentioned, that's exactly what I'm talking about. It's arguably the most important transformation that is happening in near human history. So we are living in an incredibly exciting time. So I want to share some perspective around that. But before I do that, when my slides come up here, am I going backwards? There you go. Before I do that, I actually wanted to start with a little story about what inspires me about technology and how I think about technology. So my travels take me to a lot of places, meeting customers, partners, employees. One of my favorite places is Cambridge University, so I go there every few years to meet partners. And when I go there, I usually do a lot of business meetings, but I also visit the bookstore, because that bookstore is really nice. It actually finds print that you cannot find online, so lots of nice books there. One of the books that I read recently is this book by Erwin Schrödinger. Many of you may have read this book. He is a Nobel-winning physicist. Extremely thought-provoking book. And I read about diffusion. Most of us are engineers in this room, I assume. So a lot of people know what diffusion is. Let's talk about diffusion. If you take a container full of water and you put some colored ink on one side, left side, after some time, the whole container will become colored ink. You all learned that, there's some formulas to solve that, but in the book, Schrödinger asks the question, water consists of just molecules, right? Ink consists of molecules. So how does a colored molecule on one side know that it has to get to the other side? It's not a complicated question, but eventually it does get there, right? And of course, there's a very thoughtful answer. The thoughtful answer is, not every molecule is told what to do. Every molecule is just vibrating randomly. It's just that there are more molecules on one side that want to get to this side than there are colored molecules on the other side that want to get to this side. So if you just average randomness over time, you get uniformity. So it's these kind of insights that are super, super insightful for me, and I get inspired by technology like this. Now, of course, diffusion, you can model it using partial differential equations. We all learned partial differential equations in our college and schools, and the thing about partial differential equations is they are incredibly valuable tools for solving a number of computing problems. But they're very, very intensive to solve. You need lots of machines, lots of parallel machines to solve. What is happening now is people are finding different ways of solving these kind of problems. And they're using AI. You see two papers that I have collected up, one from Caltech and another one that was a summary from MIT, that basically said that you can solve partial differential equations in a completely different way and a much more efficient way. So the reason I'm picking this example is to let you know that this kind of thing is happening across all disciplines. There was an old way of solving a problem, and there is a new way of solving a problem. And that is the transformation that is happening. So let's talk about that a little bit. Unfortunately, these slides are a little out of order, so I'm going to go this. The reason these kind of breakthroughs are happening in all of the aspects of life is because AI has advanced. AI is actually not a new thing. Even in the 1950s, people were talking about AI. There's been concepts about AI. But over the last 20 years, significant developments happened, starting with convolutional neural networks in the 90s to stateful machines like RNNs and LSTMs that are happening in the 2000 timeframe. And the big breakthrough came in the early 2010 timeframe when cats and dogs got recognized by computers better than humans. So that's the time where the inflection started to happen, where you see AlexNet there in the 2010 timeframe. The next big breakthrough came in 2017 timeframe by this paper that was published called Attention is All You Need. And that started what we now know as transformers. And transformers are at the heart of language models. And what we know of language models in the last couple of years, everybody knows ChatGPT and other things that are happening, is just incredible. So we are at the enormous inflection phase of artificial intelligence as we speak. So how is artificial intelligence actually getting power? Artificial intelligence progress has been made because of fundamental advances that have happened in the silicon level. The exponential increase in computational capabilities in silicon is what is powering artificial intelligence. So let me give you a sense for the types of improvements that are happening here. So back in the early days, in the 1930s, 40s, 50s, when computers were first invented, the architectures were all what we call as von Neumann architectures. The von Neumann architecture, the way to think about it is, you have a machine that does some calculations, you have some memory that stores what needs to be computed on. So you read from the memory, you do some calculations, and you store back. And you keep repeating that. And what happened is, machines became faster and faster and faster, so the number of things you can do this, like read, compute, store, became significantly faster. You went from 5 megahertz to 100 megahertz to 500 megahertz to 5 gigahertz. But what happened during the journey is we started plateauing. There was no place to go to 50 gigahertz. It's just become a plateau in terms of amount of computation you can do in the same way. So that's when people said, hey, why don't I put more and more processor cores? So that became multiple processor cores. So the frequency stopped, but we started putting more processor cores. And in the 2010 timeframe, heterogeneous architectures, which are much more parallel, which are called GPGPUs, started coming out. With GPGPUs, you can compute so much more things in parallel, and that's a fundamental difference from how von Neumann architectures computed, which is sequential. So the rise of artificial intelligence, the power of artificial intelligence, has been made possible by a fundamental shift in how computing is happening underneath it. And that fundamental shift is you went from doing things in a sequential fashion to a lot more parallel fashion. And that is what is powering today's artificial intelligence machines. And then if you fast forward to the right of this chart, we are now seeing what we call as the rise of domain-specific architectures. They are incredibly parallel architectures, but they're also specific to solve artificial intelligence problems. David Patterson at Berkeley has famously said that we are living in a golden age of computer architecture. So there's so much innovation happening in computer architecture that is powering these kind of artificial intelligence technologies, and which is in turn transforming life. So what I'm going to talk next is to walk you through about some of those transformations. Because we went a little out of order, so I'm going to go back to this page. At AMD, we are building computing platforms across a number of domains. We build CPUs, we build GPUs, we build FPGAs, and because of what we do, we have had our own share of technology innovations. We build some of the most complex chips on the planet. We've done the first integration of CPUs and GPUs together. We built the largest FPGAs. We built chips in 2.5 dimensions, and now in 3 dimensions. We are putting chips on top of chips and connecting that. To give you a sense for the complexity of these chips, if you look to the far right on this chart, the most capable AI inference accelerator that we introduced in December last year has 150 billion transistors. And so it's just an extraordinary amount of compute that is built into the machine like that. And these class of machines is what's making AI possible. So let's take a look at where AI is being used. At AMD, we also have the privilege of talking to customers across a wide range of markets because of the broad compute portfolio we have. We talk to customers that are in the largest clouds. We talk to customers that are in the endpoints. If you use laptops, chances are you have an x86 processor. We are one of the leading providers of that. You may be using graphics cards that are playing games, and they're also AMD graphics cards as well. And we service, through the acquisition of Xilinx, a huge number of embedded markets. Embedded means automotive, communications, healthcare, transportation, a variety of markets like this. When we talk to customers, when I'm on the road a lot these days, when I talk to customers, almost all of the conversations are about AI. What customers are trying to do, what people are trying to do, is take the types of computation that they have done in a traditional way and say, how can I do this better? And change it to an AI-based compute. Just like I showed you a partial differential equation earlier on, and you can solve it with AI, it's the same thing. We have, as an example, some of the most important front camera processing. Many of you probably drive cars with driver assistance. So pedestrian detection, lane departure warning, right? Your steering does something when you go off thing. So that used to be done with a traditional computer vision algorithm. Almost all of those types of algorithms are now being shifted to AI processing. And that's the sort of thing that's happening across all industries. So what I'm going to do over the next few minutes here is to help you understand across these different segments the types of transformations that are going on. So let's take a look at what's happening in the cloud. All of us use the cloud. Whether it's known to us or unknown to us, we service all kinds of applications in the cloud. Billions of users use the cloud. Whether it's a shopping that you do and a recommendation that's being made, whether it's a video that you're watching and a recommendation that goes along with that video, whether it's play or whether it's work, the cloud services billions of users. And the cloud is fundamentally getting a lot more AI. Let's start with what's happening with ChatGPT. That really was a point of inflection. Many of you know that it was the single most and the single fastest consumer application that was ever deployed. 100 million users in a couple of months, right? That's the ramp that we saw in that. And that was just the beginning. Now, those sorts of language models are getting agentic capabilities, which means they're not just talking to humans, they're going to talk to themselves. There was a nice paper that was published by Stanford a few months back, where the research was they created a few language models and they connected them. They're not talking to humans, the models are actually connected to themselves, and they asked these models with different capabilities to go ahead and plan a Valentine's Day event for a village. And the models basically created the entire event. They planned the menu, they sent the invites, they organized the whole event, and they learned how to do this, right, without necessarily getting taught. So these sorts of emerging capabilities are actually what is happening in the cloud. What's also amazing in the cloud is people realize that it's these sort of language applications, but a whole host of additional applications. For example, we do a lot of sustainable computing that is serviced through the cloud. Vestas is one of the famous customers that operates windmills. And the windmills controls are complicated algorithms. Those types of algorithms run in the cloud, and they're getting transformed to being in AI. So the cloud is just like completely getting transformed by what is happening with AI. So if you then sharpen your focus on the most demanding computers on the planet, they are supercomputers. We were very fortunate to have innovation that led to the fastest supercomputers on the planet. We currently have an AMD machine called Frontier that is the fastest supercomputer. It's a 1 exaflop computer. Just to picture that in mind for maybe some of the non-technical folks in the audience, that's 1 billion math operations every second. And that machine is the fastest supercomputer on the planet. It has a scaled out configuration of GPUs that power it. Why is that kind of computational capacity, computational power important? Because you can do things that were just impossible before. To give you a very realistic example of how you can relate to it, COVID-19 research to find the vaccine requires computational capacity like this. And Lawrence Livermore Labs, in a previous generation of an AMD GPU, ran COVID-19 simulations. So this is not just you're having computation for the sake of computation, right? It's fundamentally transforming our lives. And it's not stopping here. We are on track to deliver the next set of GPUs that will power what we call as El Capitan at Lawrence Livermore National Labs, that we believe will be the fastest supercomputer, twice the speed of the current supercomputer. So that innovation pace continues in various domains. If you look at other domains in the embedded space, a big area that I am truly excited is healthcare. Whether it is genomics, finding personalized medicine, or diagnosis, for example, improved ultrasound and radiation and radiology type of applications, or minimally invasive surgery. These fields are getting transformed as well. Let me give you one example. Intuitive Surgical is one of the most promising companies in the valley. They do minimally invasive surgery. A friend of mine told me that he went through a procedure. If it was done through a traditional surgical procedure, he would have taken him a few months to recover. But he was back at work in a few days because of what the robotic surgery was able to do. And these robotics aided surgeries have computation that is built based on these kind of platforms. So it's extremely, extremely powerful as you think about how it can transform life. So let's look at some other vectors. If you thought that all of this is happening only on Earth, not true. It's actually happening in space. It's actually happening all the way in Mars. For over 20 years, we've actually powered space exploration. The Mars rovers, the 4 missions are listed here, all carry some kind of AMD platforms. What they're doing investigation for the future. Why these kind of missions are powered by electronics like this is because these electronics need to have different characteristics. They need to have rugged. In space, you have cosmic ions that are hitting electrons. And the capability of the electronics underneath needs to be such that they need to survive these cosmic electrons and still do the job. You need to look at images, you need to do analysis on those images, you need to analyze the chemical composition to see if there may be water, there may be other sorts of things, and then bring it back to Earth. And these machines need to be living there for 10 years. They need to be having algorithms that can be upgraded over the air. So for example, a new algorithm came, the machine is sitting on Mars, how do you upgrade it? You need that kind of capability. So it's different kind of electronics, different form of innovation, but powering space. It's happening in space as well. And I'll bring it all the way back to the user in the personal space. If you look at your personal computer, that is getting transformed as well. Last year, we introduced a dedicated AI processor that is integrated into an x86 machine for the first time in the industry. That means you're using a laptop, automatically a number of AI functions are getting invoked. Maybe you don't even realize. Many of you may have used Teams. Anybody use Teams for doing video calls? Yeah, so many hands up. If you're using Teams and if you're on an AMD laptop, you're already using AI. Why are you using that AI? Because if you run algorithms like blurring your background or changing your eye to contact your camera, it's extremely battery intensive to run it on a CPU. So in the past, all those algorithms used to run on a CPU, those algorithms are now changed to AI algorithms, and they are now running on dedicated AI accelerators. And that's just a collaboration, but it's also happening on productivity, generative AI. So if you're using your applications like Stable Diffusion or language models, they're not just running on the cloud now. Their capabilities are coming into the PCs in the form of what we call as NPUs, neural processing units. And we did the first introduction of such an NPU into an x86, and we see an incredibly bright future for how the PC is getting transformed. We call it the transformation of the PC from a PC to an AI PC. And that transformation is going to happen this year and next year. So if you're going to buy a PC sometime soon, you look out for an AI PC. So I'll stop here in terms of the types of examples that I want to walk you through. Hopefully, it gives you a feel for how traditional computing is changing to AI computing across the cloud, a number of segments in the enterprise, all the way to your endpoint devices that you hold in your hand. We at AMD believe that we also have taken an open approach. Not only do we build the computing platforms, but we also partner with the ecosystem, whether it's in the hardware side or the software side. Because what we believe is if you partner well together, you can go a lot faster towards that future. I'm super excited by what the future holds in AI, and I hope you are too. Thank you.
Thank you, Vamsi. Can you stay on the stage for a minute? Vamsi, can you stay? Well, the speech is very illuminating. Thank you so much. Now let's welcome Li Bo and Yan Shu to the stage to present a flag. Ladies and gentlemen, let's give another big round of applause